Hi everyone, welcome to this video on lesson 11 of the Forces and Space scheme of work. This one is about moments and levers, and really I should have put moments and seesaws because all of the examples that we're going to look at today are kind of related to seesaws. Now the reason this is in here, apart from it being linked in the national curriculum and specification at GCSE and so on, but the reason I put it here in particular is because it's really just building on this idea of balanced and unbalanced forces, but we're just talking about balanced and unbalanced turning forces or moments. Now there's obviously this added layer of complexity in that it's not just dependent on the force, but it's also dependent on the distance. That said, it's pretty intuitive. Students tend to kind of get what's going on here. The purpose of this lesson is to give them a more rigorous and structured way to think about what's going on. And I think the best way to do this is just do loads and loads of examples, and you'll see in the slides, it's just endless examples for them to do on whiteboards. And I think here is a classic example of where using the concept is that means knowing the concept. If students can use it in application to a real example, well, we can be pretty confident that they know it. So I would start by telling the story, and we're going to draw a lot of little diagrams here. And again, I'm going to do this all in my book, but you could get them answering using fingers up or on whiteboards as you go through here. This doesn't all need to be teacher model without any interaction. The more you can check for understanding, the better. So I'm going to start with this. I'm going to say, okay, let's imagine my son and I go to the playground and we go to a seesaw. So my son sits at one end, and at this age, I'm going to sit at the other end. At this age, my son is 15 kilograms, and I am 60 kilograms. I'm saying that to make the numbers easier. And we're both sitting 4 meters away from the pivot. And pivot is a word that you will need to teach them. That's the pivot there, so you might want to label that as well. But we're not going to label that again after this example. So they're both 4 meters away from the pivot. What would happen? And hopefully the students will recognize that if the heavy person and the lighter person sit the same, well, we've got unbalanced moments here. And if we've got unbalanced moments, then just like with unbalanced forces, we get a change in motion. Well, if we've got unbalanced moments, we get a change in motion. And what happens is the seesaw moves down to there. So what we're then going to think about is, okay, well, then I decide I want to balance the seesaw with my son. So I'm going to draw the pivot in the middle there. My son is going to stay at 4 meters. So he's 15 kilograms. And I'm going to move along here. Now I'm just going to move like I would do in the playground. I rarely turn up at the playground with a meter ruler. That would be a bit strange. So what we're interested in as physicists is thinking, okay, if my son is still 4 meters away, how far away am I if we've managed to get the seesaw balanced? If we've managed to effectively get the turning forces or the moment balanced? Well, we can use a similar kind of method to ones that we've used before around weight, mass and gravity, because like that example, this is really just about proportionality. And what we can say is this. We can draw, I like the curly arrow method. We can say, well, look, this mass is 4 times bigger. Now, again, you can ask students, do you think the mass, and I would do question with thumbs up, thumbs down. Sorry, do you think the distance to the pivot is going to be 4 times bigger or 4 times smaller? Hopefully, they're not going to tell you 4 times bigger. I think students get that the heavier person is going to have to move towards the pivot because we've all used a seesaw, or most people have used the seesaw. So when you are modelling this, you can really emphasise that. Don't overthink it. We don't need to go into loads and loads of math here. This number has got to get smaller. And how many times smaller? Well, it's going to get 4 times smaller. So I'm going to divide by 4. And then again, you could do fingers up, show many fingers. Well, it's 1 meter, okay? So the distance here is going to be 1.0 meter, like that. So the next example I could do is maybe a year later, let's say. So here's my pivot. And now my son is 20 kilograms. And I am still 60 kilograms. And again, you'll see we're just going to mix it up here and just keep doing different kind of ways of thinking about this. So I'm 60. So we tried it again, and I sat at the same spot that I did last time. I sat at 1.0 meters from the pivot. But then we found my son had to move. So the question here is, how far away from the pivot is my son going to have to sit this time? Because it's not going to be 4 meters. And again, now we're just doing the same thing in reverse. We're going to say, well, that has got 3 times smaller. So this, is it going to have to get 3 times bigger or smaller? It's going to have to get 3 times bigger. So the answer here, this person's going to have to sit 3 meters away. Then we could look at another example. Sorry, I'm just checking my notes that I made. So then we could look at another example. Let's imagine we go down another year later, maybe a couple of years later, down to the same seesaw. And in this example, my son is 35 kilograms. I've put on a bit of weight, so now I'm 70 kilograms. And we try it this time and we think, okay, we're both going to sit 2 meters away. Doing the arrows, but anyway, you get the idea. We're both sitting 2 meters away. So what's going to happen? And again, you want to bring in this idea that now the moments aren't balanced as they were in these two examples. So in these 2 examples, I beg your pardon. So we're going to get this clockwise motion again, like that. So we can do the same thing. We can say, all right, well, what's going to happen next is, there's a lot of drawing to do here, isn't there? And again, you might not wish to do all these. You might want to get straight to the whiteboard sooner, but I'm going to go through quite a few here. Let's say now my son, who is 35 kilos, sits 3 meters away this time. Sorry, I've missed a 5 out there. 35 kilos. And I am 70 kilos. So how far away am I going to have to sit from the pivot? And again, just modeling the same process. This is the kind of thing you might want to do. By this point, I think they could be doing this on whiteboards. So that's times 2. So that's going to be divided by 2. And that's going to be 1.5 meters. So that's another example based on the same thinking. Now, one that might throw them a bit is if you switch up from talking about mass to talking about weight. So we could do another example and say, okay, it's another year later, or maybe 6 months later. So I'm going to draw my pivot again. So now I'm going to draw it like this. So I'm going to sit, what was the example I did before? I'm going to sit over here. And now, instead of thinking about mass, I'm going to think about it in terms of force, which strictly speaking is more correct. Although, because G is constant, the principle is basically the same. So now I'm 800 newtons. So this would be useful, and the examples that you'll see later involve different forces, so I think it's really important to model these. So in this case, I sit 2.0 meters from the pivot. Now, if to get balanced moments, to get the seesaw balanced, my son sits over here and happens to be 4 meters away, what must be the weight of my son? So you can see it's exactly the same principle, and students will probably be able to spot it without you modelling it, but it's worth going through it just because the principle is the same. So in this case, well, look, what's happened here? I've times this by 2, so what's going to have to happen to my force? I'm going to need to divide by 2. So in that case, I can say my son now has a weight, and perhaps I should have done that smaller, but okay, I think you guys will get the idea. My son has a weight of 800 divided by 2, which is 400 newtons. So hopefully this is making sense. The point here is that we can do moments calculations without having to do loads of difficult looking algebra that frightens students. Actually, we can just think about it geometrically. The last one I might do would be to say, Okay, now, many years down the line, my son and I go to the park together. For me, I have to imagine this because my son's only 3, so he's quite a way off this scenario. But let's imagine we both sit 3 meters from the pivot. I know I have a mass of 800. To balance the seesaw, what must the mass of my son be? And you could do, times 1 times 1, but I think students will spot pretty easily that if you've got balance moments and the distances are the same, sorry, that's not 800 meters, that's 800 newtons, then this must be 800 newtons as well. And again, loads and loads of those examples. Use whiteboards, use fingers up if that's easier. I think you don't need to give loads and loads of definitions in this lesson. I think if you're just doing loads of examples and getting students thinking, and using that concept, that's a pretty good way of getting them to learn physics, rather than worrying about whether they can recite back to you the law or the principle of moments and give definitions and so on. So hopefully that's clear. In the next lesson, we come back to our more typical force diagrams, and we start looking at drag forces and thinking about objects that are moving with balanced forces and therefore moving at a constant speed.